All right, so today we're going to be concentrating on the cell membrane. And remember that the main function of the cell membrane is to regulate things going into or out of the cell. So there are two basic ways that the cell membrane can do this. One is by using passive transport. Passive transport, and there are a couple different kinds of passive transport. Passive transport does not require an input of energy. It relies on the natural energy that atoms and molecules have. It relies on the natural energy that atoms and molecules have. So remember when we drew the atoms, we talked about how the electrons are always in motion and we can't predict where they're going. Okay? That gives the atoms this natural energy. They're always jiggling. And so because they're always jiggling, they're bumping into each other. And this is how passive transport works, using that energy. So one type of passive transport is diffusion. Diffusion is the movement of solutes. Now recall we've seen that word before. Solute means things that are dissolved in something else. So the movement of solutes from an area of greater concentration to an area of lesser concentration. And they will continue to move, these solutes will continue to move until they reach equilibrium, so that there's an even distribution of the solutes. Catherine? Equilibrium, which is an even distribution of the solutes. So for instance, if we stuff the entire student body in my classroom, close the doors. You have your natural energy, you're going to be bumping against each other, get out of my way kind of thing, right? And as soon as we open the doors, what's going to happen? People are going to leave, right? We're going to kind of flow out. Now, we might not reach equilibrium, we might not be evenly distributed, but it's the same idea. We're going from higher concentration to lower concentration, okay? Spread out a little bit. We'll take a look at what I call diffusion problems here in a little bit and see exactly what's going on here. But that's the basic idea. Now remember, we're talking about the cell membrane. What is the cell membrane primarily composed of? What kind of molecule? Those little jellyfish-looking things. Phospholipids, right. So when we're talking about diffusion, we're talking about diffusion through the phospholipids. So they're going through that phospholipid bilayer. The solutes are moving through that phospholipid bilayer. A second type of passive transport is facilitated diffusion. Facilitated diffusion is the same as simple diffusion, that's how I refer to regular diffusion, except now the solutes are moving through the proteins of the cell membrane. So instead of moving through the phospholipid bilayer, they're moving through the proteins of the cell membrane. It's the movement of solutes through the protein of the cell membrane. Still moving from greater concentration to lesser, that rule still applies. It's just that they're moving through the proteins instead of the phospholipid bilayer. The third type of passive transport is osmosis. Osmosis deals solely with the movement of water across the membrane. So we don't talk about the concentration of water because water is not a solute. It's a solution, or a solvent, I should say. Okay. But the idea is still the same. Water moves from where there's a lot of water to where there's less water. From where there's a lot of water to where there's less water until it's balanced out. So when you hear people say, oh, I slept on my textbook, so I learned by osmosis. Unless they were seeping water from the textbook, that's not true. They're seeping knowledge that would more likely be diffusion. They learned by diffusion. Probably doesn't work very well, but what we want to take a look at here is how does osmosis affect a cell? So how does that movement of water affect the cell? And in doing this, we're going to take a look at 3 scenarios, and we'll also take a look at diffusion and how diffusion works. So we'll just tie it all together. All right. So here is a reminder of the cell membrane structure. We have the phospholipid bilayer with the proteins randomly in between. So as I said, we're going to take a look at 3 scenarios. We're going to take our cell, and we'll start with an animal cell. So this is a cell without a cell wall. So we'll start with that, and we'll go back later and take a look at those that do have a cell wall and how it's different for them. But for right now, we're going to concentrate on animal cells. And our first scenario, we're going to take our animal cell and we're going to put it in a hypertonic environment. means, what hypertonic means, is that the environment has a higher concentration of solutes than inside the cell. Higher concentration of solutes outside, I guess I should put that, the environment, so I'm going to draw my little animal cell, and inside of my animal cell, there is some sodium chloride, about a 10% solution of sodium chloride. There's also some glucose, which is that usable blood sugar. And then we'll throw some protein in here too. So there's inside of my cell. Albumin is a protein. It's kind of a fun protein. It's found in eggs. And so the really old pregnancy tests, over-the-counter pregnancy tests, tested for albumin in the urine, because if your egg had been fertilized, you'd have albumin in your urine. The biggest problem was, though, that eggs that you eat have albumin in them too. So if you'd eaten a bunch of eggs and then take a pregnancy test, it might be a false positive because you'd still have albumin in your urine. So they don't test for that anymore. They test for hormones. But that's my fun little albumin story. All right, so I am accounting here for 40% of what's inside the cell. What is the other 60%? Water. Okay, out in my environment then, I still have some sodium chloride, some salt. I have some glucose. And I have some albumin. So once again, I'm accounting for 45%. What's the other 55%? Water. As we said before, there's water inside the cell, there's water outside the cell. So taking a look at these individually, let's take a look at diffusion individually. So if they're moving from greater concentration to lesser concentration, just looking at the numbers for NaCl, is NaCl moving into the cell, out of the cell, or is it staying the same? Into the cell. Here's a few intos. We're going from 15 to 10. And then that would stop when it reaches equilibrium, when there's an even amount of NaCl inside and outside. But all we're concerned about is it moving in or out or not. Okay. Glucose, is it moving in or out, or is it going to stay the same? Going from 20 to 15. Very good. Albumin, in, out, or stay the same? Out. Oops. Now, water is the really, really important one. Okay, so now we're talking about osmosis, because water is going to have an overall effect on the cell. So what is the water going to do? Is it going to move in, out, or stay the same? Out, because it's going from where there's a lot of water to where there's less water until it reaches equilibrium. Well, if water's leaving the cell, what's going to happen to the size of the cell? It's going to shrink, and that's called, it crenates. All right, so that's one possibility if we put this in a hypertonic environment. This is not ideal for animal cells. They don't want to shrink up. If they're shrinking up, they can't function as well. So let's try a different environment. Let's put them in a hypotonic environment. So we'll go get a new cell, a fresh cell, and we're going to put it in a hypotonic environment. In a hypotonic environment, the concentration of solutes is lower on the outside in comparison to the inside. So I'm using the same kind of cell, so the inside environment is going to be the same. Okay, so that's 40%. What's that other 60% again? Water. And then outside of my cell, I have those same things again, just in different quantities. And what's the other 70%? All right, so once again, taking a look at each solute individually, and then we'll do osmosis. So NaCl, is it going to go out, go in, or stay the same? Stay the same. Now, is it still moving? Yeah, it is, but you just can't tell the difference in concentration. So it's moving out at the same rate it's moving in. So I'm going to do a double-sided arrow to show it's staying the same concentration, but the molecules still are moving. What about glucose? In, out, or stay the same? What about albumin? Okay, so good diffusion going on there. What about water? In. And so what's going to happen to the size of the cell because of that water? It's going to increase in size, and if it gets big enough, it will lyse. It will break open.
So is that lyse the same we see in
Lysosomes, and what do? They break stuff down. Yep, that's the same lyse. Okay, this is not ideal either. We don't need our cells exploding, do we? That's not so good. So let's try one more possible environment here. Let's try an isotonic environment. In an isotonic environment, the concentration, now this is total concentration of solutes, outside the cell is equal to the total concentration inside the cell. So once again, we're going to grab a brand new cell since we broke that one. Let's see, 60% water. So same cell, same kind of cell that we've been using in all the scenarios. Now remember, I said total solute concentration is what's counting because once again, we've got 40% concentration outside, so 60% is water. So sodium chloride, is it going to go into the cell, out of the cell, or stay the same? Okay, it's going to go from higher concentration to lower concentration. Ella.
So when it's talking about the solute concentration in the outside equals the concentration on the inside, why wouldn't there be the same amount of like glucose?
It's the total concentration. Oh. So when we add those up, that still adds up to 40, inside and out.
Okay.
Excellent question. That's why I skewed it the way I did. All right, glucose into the cell, out of the cell, stay the same. Out. We go from 15 to 10. Albumin? Stay the same. So I'll do my little two-sided arrow because it is still moving. And what about water for osmosis? It's going to stay the same. Is it still moving?
Yes.
Yes, it is. Emma.
So kind of relating to Ella's question, like with the total composition, can you kind of tell that by the amounts of water in the cells?
Yes.
Okay.
Yes. Because remember, the water is what's going to tell us what the cell is going to do.
Okay.
So if water is not moving into or out of the cell, how is this going to change the cell size? It stays the same. It's not. And so this is ideal situation for cells without cell walls. This is the ideal situation for cells without cell walls. Questions, problems? Anything? Okay, so what if a cell has a cell wall, like plant cells? Let's take a look at those just very quickly here. So we're just going to, for the sake of not spending a lot of time on this, so this is for cells with cell walls. For instance, plants. Those are the ones with cell walls. We'll talk about them in the most detail. Now, if you recall from your diagram, the cell walls of plants are on the outside of the cell. So we have cell wall, And then inside of that is the cell membrane. Inside here. So the cell wall is rigid. The movement of water into and out of the cell isn't going to have an impact on the cell wall, but it's still going to have an impact on the cell membrane. So we had our three scenarios. So let's just kind of recap what happened in each of those scenarios. And then we'll take a look at how that affects this cell with the cell wall. So if I go back all the way up here, in hypertonic, the animal cell shrunk, it crenated. So in a hypertonic environment, the cell shrunk. Once again, go back up here. In a hypotonic environment, the cell grew or possibly lysed. Now, lysing is not going to be such an issue because of that cell wall. It's not going to allow it to break, but it can grow. And our last scenario, an isotonic, it just stayed the same. Nothing changed. Well, what we see in cells with cell walls, in a hypertonic, okay, so the water is leaving the cell. The cell membrane pulls away from the cell wall. So this is hyper. It shrivels away from the cell wall. And so it kind of pulls on the cell wall, making the cell wall weaker. So it pulls on the cell wall and makes the cell wall weaker. Just going to bring this down with us so we can keep an eye on it while we're in a hypotonic solution, oops, that's a really weird looking plant cell, but okay. This is a hypotonic solution. So water is coming into the cell. That cell membrane hugs up against the cell wall, pushes against the cell wall. And gives it strength. In our last scenario, this is pretty much what I drew in the very first drawing of the plant cell there. The cell wall is not exactly pulling away, but it's not hugging, or the cell membrane is not hugging either. It's just kind of hanging out inside of here. And so this is what we see as a wilted plant. So which of these three scenarios do you suppose is best for plants? What do you think, Annie? Say that again? Hypotonic. This is ideal for plants or for cells with a cell wall. Any questions? We're good. Okay. Then back to. So the other type of transport that can occur across a cell membrane is active transport. Active transport requires additional energy. Because this time we're moving from an area of greater concentration, of lesser concentration to an area of greater. We're moving from an area of lesser concentration to an area of greater. So we're moving against the concentration gradient. We're moving against the concentration gradient. We're going from lesser concentration to greater. So there are a few forms of this. I'm only going to mention two of them because they're really the ones that we touch on the most in this class. Exocytosis. Exocytosis is when the cell releases substances from vesicles So we'll watch a very, very short, it's like 2 minutes long video on this double block day at the very beginning of class, showing how this works. But basically the vesicles attach to the cell membrane and burst open, releasing whatever inside of them out into the environment. We talk about this a little bit, not a whole lot, but a little bit in this class later on. The one that we do mention more is endocytosis. And endocytosis is when the cell basically engulfs substances that are outside of the cell. engulfs substances that are outside of the cell and brings them into the cell. The cell engulfs substances that are outside of the cell and brings them into the cell. So it's the opposite of exocytosis. There are two types of endocytosis. I really only want to mention one of them because there's really only one that we continue to talk about. I'll mention the other one. Okay, phagocytosis. Phagocytosis means cell eating. And so, for instance, later on in the year when we talk about like the immune system and talk about the cells, we have lots of phagocytes that digest, they eat and digest foreign bodies that get into our bodies. So I'll mention that one. The other one I'll mention because I think you'll probably see the word. The other form of endocytosis is pinocytosis, which literally means cell drinking. So when the cell is engulfing, it's engulfing water.